Welcome to this lecture series in real analysis. In this lecture, we'll finally define what are real numbers and say a few things about them. So, what we need to know is what are rational numbers, and we need to know the notion of least upper bounds. We saw that there is a certain deficiency. I called it defect. Well, it's not like there is a defect in rationals. It's not like rational numbers do not work or there is something wrong with them. No. It's just that they lack a certain property that we wanted them to have. Okay, so there is a deficiency in rationals, which we noticed, meaning things, you can find subsets of rationals which have upper bounds, but no least upper bound. Okay, then we defined ordered fields, which capture all the properties of rationals that we learnt about. So all the algebraic properties and all the order properties. So that is the abstraction of rational numbers. And then we saw that there is a natural copy of rational numbers in any ordered field. Having said that, the only example of an ordered field that we know of is, as of now, is the rational numbers. So far, hence, we haven't said anything of content here, but we are building to it. All right. So here are some problems for practice. And now let us get started. So I have written something down already, which I should erase and write down again. Okay, so I will write this down again. So the real number field, or I should say a real number field, at the moment I cannot say a real number field is an ordered field denoted this way. So this is just a new symbol, which is an R with a vertical bar accompanying it. So it's an ordered field such that certain property is satisfied, which is just the insistence that whatever we lacked in rational numbers, we do not lack in this hypothetical ordered field. So let me write that down, such that for all non-empty subsets, S of our field which have an upper bound also have a least upper bound. So we just demand the property that we lacked in rationals to be satisfied in reals. Now, of course, just because we can define something or demand something doesn't mean such a demand can be fulfilled. So the first thing to say is that, yes, there is such an ordered field. And that is the topic of next lecture. In the next lecture, we will construct by hand what are or at least a field of real numbers. We will construct an ordered field which satisfies this property that everything that is bounded above also has a least upper bound. Okay. Having said that, let me plant a flag here that even though we will construct this by hand, the construction per se is of no use. Meaning the gory description of this thing that we will do in the next lecture is of no use. What is of use is really the definition. Okay? So fine. But the other important question is, how many such fields are there? After all, this is where we will developing all the calculus on. We will be developing calculus on the real numbers. So how many such fields are there which satisfy this property? That is a very important question, because if there are multiple such fields, then every such field would have its own calculus, and there would then be many calculuses or calculi. So it's an important question, and the answer is actually there is only one such field. Now, in what sense there is only one such field? Suppose we had such a field, then one can say that, well, just decorate every element of this with a hat, and then it, becomes a new field in some sense. As a set, it looks different because you have, in some sense, changed the names of the things there, so it is a different object. But in a sense, nothing has changed, as we should intuitively feel. Just because you put a hat on everything, that shouldn't change anything. So in what sense is it unique? Let me elaborate on that. So what I'm trying to say is that if we have this and that are real number fields, which again is defined above, then there is a bijection phi such that phi respects the arithmetic or the algebra as I call it, and the ordering, and one more little thing, such that respecting the addition, respecting the multiplication, preserving the multiplicative identity, perhaps insisting this is not required, but it's not wrong to put some redundant thing. You might be able to derive this from that, I don't know. Perhaps you can. I haven't even thought about it, but it's just good to put it there. And lastly, it preserves the order properties. So it preserves the arithmetic and it preserves the order properties. So everything of essence is preserved. So things here, after you change their names using phi, behave exactly like things in R prime. So there is no essential difference between this object and that object. Okay, so I hope that was clear. So in this sense, the real number field is unique. Everything that you can do here, you can do there, and everything you can do there, you can do here. And one last comment, even though this is an abstract looking definition, we have an ordered field and whatnot, and then we have some property, we will think of the real numbers as we used to in high school. How did we think of it? We used to draw a line, somewhere mark the origin, and then the usual business. We mark out the integers in them, and then the midpoint of this guy is what? I don't know, 2.5 and so on. 2.5 meaning 3 by 2, not 3 by 2, 5 by 2 and so on. So this is how we think of them, and in the light of what we saw in the last lecture, that every ordered field has a natural copy of the rationals, this is not so far away from the truth. Right? This picture is not misleading, is what I'm trying to say. There is a natural copy of rational sitting inside our real number field, and because of this property, the gaps that are there in rationals are filled, if I may say so. Okay, so this might take some time for us to digest, but just hang on, and in no time you will become comfortable with this kind of abstract definition. And moreover, it is important that this is what matters. We cannot get around this. This is what matters. The exact construction is irrelevant. All right. So let's look at few more concepts, which are not really new concepts, but they are terminologies which we will be frequently using. So it's a good idea to spend time on it. So fix a non-empty subset of the real numbers. So now we have our real number field. We have seen that it exists and is unique, even though we haven't proved any of that. The unique real number field we will denote by this symbol, and it has an ordering. So all of that is there, and now once we have a non-empty subset of it, the supremum of this non-empty subset is defined as two cases. If A has an upper bound, then the supremum is defined as the least upper bound of A. And if it is not bounded above, then we just write notationally, there is no meaning to it, we just write that this is equal to this symbol. Now this symbol can invoke a lot of feelings and emotions in us because of so much lies, because of so many lies that are spread around it, as if this were some great mystery. As of now, this is just a symbol. This has no meaning. Writing this is same as saying A does not have an upper bound. And when A has an upper bound, then we just define supremum of A as the least upper bound of A. So supremum is just another name for least upper bound, except that when you do not have a set that is bounded above, still you can use the notion of supremum without any extra content. It's just that we record via a symbol that it does not have an upper bound. That's all. Okay. Now, just like we have the notion of least upper bound, we have the notion of greatest lower bound, right? So let me not write down the formal definition. If you know the definition of least upper bound, you can easily come up with the definition of greatest lower bound. Basically, it is a lower bound that dominates every other lower bound. That's all. So if you are still unclear about it, consult some book or Google around. You will get this. And now we can define the infimum. So fix a non-empty subset of the rationals. Sorry, what am I saying? Fix a non-empty subset of the real number field. The infimum of B is defined as verbatim as above, but the above will become below and so on. So if B is bounded below, then infimum of B is defined as the greatest lower bound of B. And if B is not bounded below, then we define the infimum of B as minus infinite. Now, it's not like there is some algebra happening here. It's just another symbol. Of course, you can think of infinite. If this is the way you think of real line, you can think of infinite as something sitting over here and minus infinite as something sitting over here. But do not think anything more than that about it. Okay. All right. So let's do one final thing, or maybe, yeah, we have to do this, get this out of the way. It's a very, very simple statement, but since this is the first time we are doing something of this sort, perhaps it's a good idea to do everything in full detail. So what are we saying? We are saying that suppose we have a subset of the reals which is non-empty, and if it has a lower bound, then it admits a greatest lower bound. Okay, so does this need to be proved? Yes, because the property of real numbers that we have is that everything that is bounded above has a least upper bound. We haven't said anything about the greatest lower bound or the existence of greatest lower bound. So the fact that greatest lower bounds exist for everything that is lower bounded requires a proof, and that is what we will do. And this is a very simple exercise, but let's do it in full. So first we will collect all the lower bounds. Since B is bounded below, we can collect the set of all the lower bounds. And I mean, we could collect this anyway, but the point is, since B has a lower bound, this is a non-empty set. There are things inside it. Okay. Now note that, importantly, L has an upper bound. And this is, of course, not any mystery. Any element of B is an upper bound of L. Just realize that it's a very, very direct, straightforward statement. Okay, now since L has an upper bound, by the property of reals that everything that is bounded above has the least upper bound, we can set y as the supremum of L and y is a real number. It's not plus infinite or anything. This is not infinite because L is bounded above. So this is a real number. Okay, we claim that y is a lower bound of B. So we collected all the lower bounds and we claim that the supremum of this is also a lower bound. Okay, and again, this is not hard. So you can do this by yourself in 1 second, but still, let me bore you with the details. So fix an element of the set B arbitrarily. We want to show that this is the case. This is what it means to say that y is the lower bound of B. But we know that B is an upper bound to L. And by the definition of supremum or the least upper bound, we thus have supremum will also be dominated by B because B is an upper bound to L, which is same as writing this is the case, and we are done. So we have proven this claim. Now we claim that y is the greatest lower bound of B. Okay, so let's see why. So suppose we have some other lower bound. In other words, we have chosen an element in L. We want to show that this is the case. Showing this will finish the proof that y is the greatest lower bound of B. So here I should have written a capital B. What have I written? Yeah. So how do we do this? We have y prime is an element of L because it is a lower bound to B. Thus we have y prime is at most the least upper bound of L because least upper bound is after all an upper bound, which is equal to y. And that's it. So this finishes the proof of the two claims, and this final claim shows in particular that the greatest lower bound exists. It shows something more than what we set out to do. We actually showed that the greatest lower bound is the least upper bound of the set of all the lower bounds. This may sound like a tongue twister, but it isn't. Okay, so I hope this is clear. And here is an exercise. Here is an exercise, very simple, that let A be a subset of R and it be non-empty. Then show that infimum of A is this thing where I need to explain what is minus A. Minus A is by definition minus X, where X is in A. That's the definition of minus A. And of course, if A has a lower bound, then it will follow that minus A has an upper bound, and hence this makes sense, and hence this is a real number, and this will just be an equality of real numbers. If A does not have a lower bound, then this is minus infinite, and it will follow that minus A does not have an upper bound, so this will be plus infinite. So this has to be then understood under the convention that minus of plus infinite is minus infinite. So just that much of conventional thing is allowed, and this is then a simple exercise. Okay, let me finish this with some notations, which we are again familiar with from high school. So suppose A and B are two real numbers, and you may assume that A is less than equal to B. Okay, then we define, although this assumption is not really needed, but still. So we define this as those real numbers such that, maybe use a different color, such that this is the case. Similarly, this is defined as via this declaration, and I'm sure you know the rest. If I make a mistake, just be aware. Okay, I'm sure you were able to do this by yourself, but these are some notations that we will use. These are called intervals. This is called the closed interval. This is the open interval. This is half open, both open, but infinite interval, infinite or semi-infinite. In fact, these are called semi-infinite intervals. And then the full by infinite interval is of course the set of all the real numbers itself. Okay, so fine. To visualize, let's say that if we want to visualize the first one, it's basically this way. You have this thing denoting the set of all the real numbers, and here you have, let's say, a, here you have b. Then all the things including a and b is the first one. In the second case, it's everything in between. In the third case, it includes a but excludes b, and so on. So it's very easy to visualize these things. Alright, so let me not take more time. With this, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.